Okay, so welcome back to another video. So here's a partial sum that we like to evaluate, and that's associated with a binomial coefficient as our given. So we have the partial product of n choose k of the alternating series -1 to the power k divided by k plus 1 quantity square. So it's a little bit unorthodox, the method that we're actually going to do in today's video, because as you know, anybody that would like to typically solve problems, you start with what you're given and then work your way from there. We're actually going to do something a little bit different this time, and that is we're actually going to observe the following with, the binomial coefficient itself. So we start off by actually applying the binomial theorem. So that's actually the first hint gave away. And there's actually going to be some inputs we'll be applying to that actually helps. So the takeaway from basically is the whole goal is we're observing using the binomial theorem, but what happens in that process is that we actually get some sort of value. Well, what we're trying to calculate that value that is set to equal to this binomial, or rather the partial sum that is given to us that we want to calculate. So this is going to be a different approach. So other than that, that's the takeaway from how we're going to see it. This is actually going to come out to a very nice result. So let's just jump right in. So we start out with the binomial theorem for x and y, and then for any real numbers, and then n is an actual number. So x plus y to the power n is equal to the partial sum from n, and then, well, k is equal to 0, of n choose k of x to the power n minus k, and then multiply with y to the power k. So let's suppose that if we let x equals 1, and we're going to let this variable be t, instead we let y equals negative t. So we put in those inputs. So I have 1 subtract t to the power n is going to equal, of course, this is just the same notation over here, and then the binomial coefficient doesn't really change from here, but what does change is what we plug in for the input. So we set x is equal to 1, so 1 to any exponent is just going to be 1 itself. Then negative t to the power k is, negative 1 to the power k multiplied by t to the power k. So we have an alternating series, so that's great. So we're getting somewhere. So with this, now let's actually do a little bit of integration. So I'm going to integrate with, of course, respect to t, and we're going to evaluate this integral from both sides integrate from both sides from 0 to x. So we have 0 to x of 1 minus t to the power n dt, then equals 2. So let's see, if it's just anything does not depend on, well, for one, that we're integrating in respect to t, so everything's in constants, and then we can actually interchange the sum, so the sum can come outside. So n, k equals 0, then n choose k of negative 1 to the power k, multiply with the integral from 0 to x of t to the power k, then dt. So let's actually calculate the right-hand side of the integral. That's actually a little bit easier to deal with, which of course you could just apply the power rule, which again, I'm going to write this again, 0x t to the power k dx or dt is equal to power rule, so it's just t to the power k plus 1 divided by k plus 1. Evaluate this from 0 to x, so anything you plug for 0 is just 0, so the only thing left is just x to the power k plus 1, and then divided by k plus 1. And so now let's actually calculate this integral over here on the left-hand side. So the integral from 0 to x of 1 minus t to the power n and then dt. So let's say we do a u sub, so u equals 1 minus t, then du is going to equal negative dt. So we actually plug in all that substitution in. For 1, there's a negative, I'll factor that outside. So negative, calculate our new bounds, we get 1 minus x, and then on the bottom, if we plug in 0, so we get, not 0, it's supposed to be 1, 1 minus 0 is 1, and then u to the power n, then in the world of du. Okay, and so what we have here is, let's actually move up to the top. So we have negative u to the power n plus 1. That's basically just applying Powers' rule yet again. Then divided by n plus 1. Evaluate this from 1 minus x to 1. So that means for 1, if you notice that it's a minus and a minus, so what I'm going to do is if I plug in 1, so that's associated with after the minus, so I'm actually going to put that in the front. So this is going to be 1. And for another thing is that they also share the same denominator too when you plug in those values. So I'm going to put that together as one fraction. So I have that this is 1 minus x quantity, and then n plus 1, then divided by n plus 1. Let's actually plug all this back into our substitution for what we have over here on the left and the right. So of course, again, restating. So the left-hand side we have is 1 minus x quantity n plus 1 divided by n plus 1 is equal to the partial sum k is equal 0 binomial coefficient. Then what we have is -1 to the power k, then multiplied with x to the power k plus 1, and then divided by k plus 1. Let's actually do a little bit of dividing. Let's divide x to the both sides. So that means the x to the 1 for here will cancel. So far that'll give us 1 minus the same thing on the numerator, but now on the denominator we have an x times n plus 1. And then on the right hand side, again, nothing has changed so far, not until we reach the exponent, or rather the base of x, which is -1 to the power k, then x to the power k, and then divided by k plus 1. So let's actually do, yet again, we're going to integrate a second time. This time our bounds is actually going to be from 0 to 1. And this will actually come down to the point where, if you'll notice that, I think you can just already guess at this point, as I've said earlier, that the right-hand side is going to give us exactly what is given, and so the left-hand side is what we're going to have to calculate this entire time. What is we're going to calculate? Well, you'll see in just a sec. So let's see. So if I integrate both sides from 0 to 1, for 1, I have an n plus 1 on the denominator. I can factor that out. So we have a 1 divided by n plus 1. Then the integral from 0 to 1 of 1 subtract 1 minus x divided by, or to the power n plus 1, and then divided by x dx. Okay, then equal to, so integrate, but first actually it's just, again, summations, partial sum, again, interchange, and choose k, and then we have -1 to the power k divided by k plus 1, and then multiply with the integral from 0 to 1 of x to the power k dx. Okay, and so right hand side's a pretty easy integral to calculate, and so let me actually just put a little bit of notation, rather abbreviation, to say that we know that this is exactly just the same thing as what we did from earlier, the t to the power k, except it's just 1. What we see is that this is actually just going to equal to 1 divided by n plus 1. And then what's nice is that, well, actually this is supposed to be a k plus 1 since the constant's k, so k plus 1 over here. And so now actually performing all that substitution, you'll notice that, again, put in with the quantity, and then it gives us exactly what we want. So therefore we have to, this whole time is that this is just equal to, the exact same thing over here. K is equal 0, and choose k of -1 to the power k, and then divided by k plus 1 quantity square. Let me put that as given. And so we're just trying to calculate this integral all along. So this is actually the pretty easy integral to do. So what we're going to do is we're going to actually apply u sub. So let u equals 1 minus x. And of course, du is equal to -dx. Then we just apply everything. So again, factor out the negative from outside. So I have a -1 divided by n plus 1. Then our new bounds, not new integral, new bounds. So if I plug in the bounds, so I have a 0, and then I have a 1 over here. Then this gives us 1 minus u, then to the n plus 1 power, divided by now x. So let's see, if I just subtract 1, then the minus, so that means 1 subtract x, or u in this case. So right here. So as we see from this integral over here, we actually know that we take some observation. We see that by definition, this is the nth harmonic number. And the integral representation is written as follows. So we have 0 to 1 of 1 subtract u to the power n, and then divided by 1 minus u, then du. So making some observations over here. For 1, that we can actually switch the bounds. That becomes negative. Then that negative will cancel. And then afterwards, we have exactly what we want of that formulation. But this is actually the n plus 1 term of our harmonic number, h to the n plus 1. Then divided by the n plus 1 over here, just like that. And so there we have it. This actually just completes the final evaluation of our partial sum slash, the binomial coefficient partial sum that we started with, the binomial theorem. Make the observations we want by plugging in the terms, and then we actually get the given that we wanted that sets the integral, which we wanted to calculate this entire time, and therefore it leads to this answer just like that. So yeah, that's pretty cool if you ask me.